Today I'm going to talk about the latest result coming from my research, and specifically today I'm going to show you how to build an image of the subsurface when the data that we have available contain a lot of internal multiples, and we know that internal multiples can cause troubles when we want to use them to create an image using conventional imaging techniques like one-way downward continuation on RTM. Let me just tell you that the material included in this presentation is not in the report book, but it will be soon available through my thesis. We didn't have time to include this as a normal report, but you will all be will be available to you as a thesis. Let me start reminding why internal multiples are bad when we try to image them using conventional technique. Is because almost all imaging technique, current imaging technique, assume single scattering assumption. So they all share this common assumption, and this means that the wave bounces only once in the subsurface and then go back to the receiver where they are recorded. And this is what we call single scattering. But as we know, our Earth that doesn't happen in the Earth, and the waves bounce a lot of times internally between the layers, for example, as you can see here. And if this kind of data, this kind of wave field are included in our reflection data, if you use RTM, reverse time migration, for example, to build an image, that internal multiple will be imaged as a deeper layer, and this is because these techniques cannot distinguish between waves that have bounced once or multiple times. So we're going to show you that using a technique that we developed during my research, a technique that allows us to reconstruct the wave field originating from a location at depth to receiver at the surface, which is something similar to seismic interferometry, but we go beyond that because we do not require to have a receiver. We are not required to have a receiver at the location of this virtual source. So we showed that actually in previous consortium meetings, that we are able to retrieve a wave field which originates from a point at depth and record it to the receiver at the surface. Here I have some couple of references, papers that we co-authored in the past 2 years. So our technique, which has been described in reports and papers, and also by other students here, like student professor here, research professor Jyoti, in previous meetings, we are able to retrieve this wave field as if there was a real source at the location indicated by the red shape. And additionally, if we apply source receiver reciprocity, this wave field corresponds to the wave field that originate from sources at this acquisition surface and recorded at the location indicated by the green triangle. And we define this wave field as G stands for Green's function, originating from sources location XS and recorded and converging, focusing a location called XI, and the I stands for image or image point. And then we show you that if we use this method to retrieve this wave field at every location, then we are able to build an image free of artifacts. And let me just remind you that we need two data for our method, and these are the reflection data measured at the surface, and the only requirement is that they do not include free surface multiples. And we need a background model, which is also currently current input for all the downward continuation on RTM. Additionally, this method, our methodology allows us not only to retrieve this wave field, but also to decompose it in its downgoing and upgoing component. And let me be a little more specific about this. The blue one, indicated by G+, is what we call downgoing wave field. And as you can see, this wave field is actually not only downgoing, but it's going up and down. Or what we mean with downgoing is when it reaches the point, the image point now indicated by red triangle, at that point is downgoing. And same reasoning applies to the upgoing wave field indicated by G-, and here in red is upgoing because when it reaches the focusing location indicated by the green triangle is upgoing the location. So if I will show you that using this technique, which has been like my main topic of one of the main topic of my thesis, we are able to retrieve the wave field that is recorded the location inside the subsurface and then decompose it in its upgoing and downgoing components. And these two components will be key, and later I'll show you how to build an image that it will be free of artifacts which are often due to internal multiples. Let me show you an example of this wavefield retrieval. This is a reference wavefield. This is being computed placing a real source at that location. This is what we would record at the receiver at the surface. And now in green, we see the retrieved wavefield. So the wavefield that we will able to reconstruct using our methodology. As you can see, it matches almost perfectly, except for a small mismatch indicated by the arrow. And this is due to the fact that we have a limited aperture and that we have waves which are propagating horizontally, like refraction, which are not accounted for by our method. Let me tell you that all the traces have been multiplied by an exponential just to emphasize the late coda, which have been reconstructed very well. And this is the downgoing component, and this is the upgoing component. So once we are able to do this, we'll use these two components, as I said before, to build an image. But first, let me introduce to you the model we were going to use to show you the results. This is a model that's derived from the Amoco model. As you can see, it's symmetric. This is not required by our methodology, but it has been done only for visualization purpose, and that will be obvious in a couple of slides. And we will focus our image on the area enclosed by the rectangle. And another nice perks of our methodology that allows us to do targeted imaging. This is the velocity, and this is the density. And in both slides, the arrow indicates a layer characterized by high impedance. So it's characterized by a velocity, a density, which is higher with respect to the layers that are surrounding this layer. So this will be the major cause of the internal multiples that will be present in the data. And this is just an example of a shot acquired at the mid of the model. And the red arrow is indicating a very strong internal multiple. And if we feed this data into RTM or one-way migration, this will be imaged as a layer, which we often call as a ghost reflector. This clearly will cause trouble when we give this image to interpreters. And this is the background velocity that we use as an input for our conventional imaging and for our methodology. So let me just remind you, as I mentioned before, the two inputs needed for our method are the same exact inputs needed for migration, for RTM over wave continuation. So the data without resurface multiples and the background velocity. And This is the results we obtained using one-way migration, which is just depth extrapolation. And I want to tell you that if we would have used RTM, we'd have obtained the same result. And because right now in this presentation the focus is on the effect on internal multiples in the data. As you can see, the main reflectors have been imaged correctly, but the red arrows indicate something that we don't like. And these are the ghost reflector that are due to the presence of internal multiples in the data. As you can see, especially the middle, the arrow in the middle is pointing to a pretty strong, ghost reflector. And also in general, you can see that this image is, it's not very clean. So this is just to show you something that, of course, all you already know, is that if strong internal multiples are present in the data, this will be imaged as ghost reflector. And now this is, becomes obvious why our method was, our model is symmetric. So you can see that the main reflector, real reflector have been imaged correctly, but then there are in the middle between the reflector, we have ghost reflector, which do not correspond to real reflector. What we do now, we finally get to the really interesting part. We show you how to use our methodology that give us the up and down wave field at an image point to build an image which will be free of ghost reflectors. And how do we do this? So what we do, we take an area that corresponds to the same area that we imaged before, and at every point, indicated by now these black circles, we reconstruct, retrieve, using our method, the up and down wave field that converge to this point. And once we do this for every image point, and we do what we do a simple cross correlation, and we evaluate these at time equal to 0, and this is the image that we obtain. And you can see now the the reflector that were before indicated by the red arrows are now gone. Let me just briefly remind you what we did. So we computed, we retrieved G plus and G minus, so the downgoing upgoing wave field at every image point. We cross-correlate these two wave fields, and we evaluate result time equal to 0, and this is the result. This is again the comparison when we show the model. You can see now the reflector is still the correct location, but now the ghost reflectors are not in the image, and also the image it's way cleaner. So what we did here, we first showed that we are able, using data which includes strong internal multiples, to build an image free of ghost reflectors. We can go a little bit further and do a better job with the amplitudes. As something that I should have mentioned before, actually, apologize for going back, that there's a layer, there's a flat layer here at 2.3 kilometers of depth, which is not very well visible here. This is due to the fact that we have this ghost reflector like kind of hiding it. And this is obvious when we put next side with the true model. Here in the correlation autofocusing image, we can see that this flat reflector it's a little bit more visible. But we want to do a better job and take advantage of relation between upgoing and downgoing wave field at a constant depth level that is indicated by the equation. So at a constant depth level here indicated by Zi, at every image point on this depth level, G plus and G minus are related by this equation. And here R, the reflection response here, is the reflection response of a medium which corresponds to the actual medium below this depth level and is homogeneous above. So if we can solve this equation using multidimensional deconvolution, we retrieve R and evaluate it time equal to 0, this is the image we obtain. It's very similar to the cross-correlation image, but now we better retrieve the amplitude of the reflector. As you can see now, the flat reflector indicated by the arrow is way more visible compared to the cross correlation image and to the one-way image. And here again is the side by side with the true model. So this is are some slices of this image taken horizontal coordinate of 200 meters. So and we have one-way migration, the correlation image, MDD, and the true amplitude. As you can see, we do a way better job for the deeper reflector, where the amplitude of the MDD is definitely closer to the one of the true model, while for the one-way migration and correlation, these amplitudes are really weak. Also, you can notice something that, especially for the second reflector, the one at 1.3 kilometer, which is supposed to should have the same amplitude of the one at 1 kilometer. MDD also doesn't retrieve correct amplitude. This is due to the fact that mainly we are using a really strong, a really limited aperture. So we do not have enough energy to be able to retrieve the amplitude of this layer. This is the final comparison between, on the left, on your left, yes, the result obtained by MDD and autofocusing, and on the right, the image built by one-way migration. And here, the improvement using our technique it's really evident. So you can see that all the ghost reflector and the noise present in the image built by one-way migration is now gone in the image built using first retrieving the up and down Wavefield and then cross-correlating or retrieving the image by multidimensional deconvolution. What we show now, want to show now is that our method, it's robust with respect to error and in the background velocity used to, which is an input for migration techniques and to our method. In this case, what we did is a very simple test, and a plan for the future is to apply more complex error to this background velocity. Now we just apply the constant error of 10% to this velocity, and clearly this will when we use ground velocity to migration, all the layers, in this case since the velocity higher, will be shifted downward. And we'll do this, we perform this on a different area, and because of what just said, now the final image of this area will show all the layers shifted downward. And this is the image obtained with one-way migration. And as you can see, first of all, it's really noisy. The top reflector is being reconstructed well. The reflector in the middle, it's there, but it's not very clear, and also looks like doesn't have a good continuity. There's sign change. And the yellow circle, ellipse, is indicating a lot of ghost artifacts due to the presence of internal multiples. The red arrow indicates an artifact that is due not to the presence of internal multiples, but to a limited aperture, and this will present also in the image built with our methodology. And this is our main image. And as you can see, it's way cleaner, and all the artifacts now indicated by the ellipse are now gone. And the deeper reflector, which was clearly not evident in this image, is now better evident and visible in the image we built using the up and down Wavefield and MDD. So as conclusion, to conclude, we show that, kind of to summarize what we did in the previous years, that our methodology allows an accurate Wavefield retrieval and then an up and down decomposition. And once used, then we can use this to Wavefield to build a better image free of ghost reflector using either cross-correlation or multidimensional deconvolution. Let me remind you that in this process, we are not using any forward back propagation to build an image. And as I showed you in the last, with the last slides, is that this methodology is robust with respect to errors in the background velocity model. Of course, clearly the reflector will be still imaged at the wrong location, but the image will not be affected by internal multiples. As a future work, the first is like the idea of extending this method to receive as an input data which now have free surface multiples, and this will be the topic of the next talk given by Satyan. And also is to see how this, if this methodology will be still working, will not break down if we have attenuation, which is an important topic because our Earth presents attenuation. And this is topic of the talk that will be given tomorrow by Pablo, which is one of the visitors from Spain. And ideally, the end goal is the application of these to real data and eventually extension these to elastic waves, not just acoustic. Acknowledgement, I want to thank especially the people in Delft beside Kees Wappenaar, especially main topic of a lot of discussion about modeling, and Joost, which is here and also will be one of the next speakers. And I conclude, and I'll be happy to take any question and leave you with one of my favorite quotes.